Hello everyone, welcome you all to extra live session of NPTEL course Fluid Flow Operations taught by Professor Shubhita Kumar Majumdar, and my name is Nagafan Sai Kumar. I'm the teaching assistant for this course. So Fluid Flow Operations is a 12-week course, and we have successfully completed all the 12 weeks, and we have been through different concepts related to fluid flow operations. So today we'll try to have a recap of all these topics that we have discussed until now. And if you also have any doubts, you can ask me, like you can unmute yourself and ask me or post them in the chat box as well. I'll try to answer them. Okay. So let's try to make this an interactive session. Okay. So coming to the first week, that is on week one, we discussed mostly about basic concepts related to fluid flow operations, like different fluid properties, say density, viscosity, surface tension, compressibility. So let's just have a recap of all these things. So what is density? Nothing but mass per unit volume or mass per volume. Okay. And what is viscosity? It is measure of fluid's resistance to deformation, right? Measurement of a fluid's resistance, deformation. Then we have surface tension. What is surface tension? Cohesive force at the surface. Let's just put all these definitions in simpler way. Cohesive force at this fluid surface, right? And then we have compressibility. What is compressibility? Ability of a fluid to change its volume under pressure. Ability of a fluid to change volume under pressure. Okay. And then we have ideal fluids, or let's say ideal versus real fluids. Okay, we have ideal versus real fluids. So, what is the difference between ideal and real fluids? Ideal fluids are basically imaginary fluids. They don't actually exist in nature. The properties of ideal liquids are they're like incompressible in nature and they have zero viscosity. Whereas of real fluids, they exist in nature. They have a certain viscosity, measurable viscosity, and they're also compressible fluids. Right. Ideal fluids are incompressible and have no viscosity. Whereas real fluids, they are compressible and they also have measurable viscosity. Okay. So then we have fluid statics. So after discussing all the basic properties of fluids, then we studied about fluid statics. Okay. So under this fluid statics, we learned about different basic concepts which helps us in calculating pressure or understand something called buoyancy, stability. Okay. So first, we studied how pressure varies with depth. Pressure variation with depth. So how does pressure vary with depth? So P is equal to P naught plus rho G H. That is, so let's say if we take a container filled with water, and let's say P naught is the sorry, atmospheric pressure, and you want to calculate pressure at a depth of let's say H meters from the surface. So how do you calculate pressure at this particular depth? So you just take summation of P naught plus and the pressure exerted by the height of water. That will be rho g h. So this is going to be the pressure at this level. Okay. And then we also understood how to calculate pressure forces on surface, like whenever a body is submerged in water. So how to calculate the forces exerted on the particular body using hydrostatics. Hydrostatic forces on the surface. Okay. And then we also understood about buoyancy and stability, which was given by Archimedes' principle and its applications as well. Buoyancy and stability. Okay. So we used a same principle to calculate the forces on a dam wall, which is submerged in water. Okay. So we also tried solving that problem. And after this, we tried to understand difference between laminar and turbulent flow. Also understand. We also tried to. Just a second. I think there's some issue with the screen sharing. Okay. So then we understood differences between laminar flow and turbulent flow. Also, we discussed about dimensionless number called Reynolds number and its application. So, how do you use Reynolds number and when do you use this particular number? And then we also studied continuity equation, Bernoulli's equation. Okay, flow types, that is laminar and turbulent flow. And then we discussed about Reynolds number. So, what is Reynolds number? Rho V d by mu. Okay, where rho is density of the fluid, V is velocity of the fluid, the diameter of the pipe, and mu is viscosity of the fluid. So if Reynolds number is less than 200, what would be the, sorry, 2300, what would be the nature of fluid? Will be turbulent or laminar in a pipeline? If RE is less than 200, and then if RE is between 200 to 4000, 2300 to 4000, and if RE is greater than 4000, what would be the nature of the flow? If it is less than 2300, it will be laminar flow. If it is in between these numbers, that is 2300 and to 4000, it will be translucent, transient. And then if it is greater than 4000, it will be turbulent flow, right? And then we discussed about continuity equation. So what is continuity equation? Just give me the equation. In a continuous flow, A1 V1 will be equal to A2 V2, right? So A is area, V is velocity, and this is at two different locations. So let's say if we have a pipe of some converging session, okay? So let's say area at this point 1 is A1 and velocity of the fluid at this location, that is point 1, be V1. And if A2 and V2 are velocities, area and velocities at location 2, so we can write using continuity equation, A1 V1 is equal to A2 V2, right? Because flow is constant, Q will be Q1 is equal to Q2, right? So from there we can write A1 V1 equal to A2 V2. So we can also write this as AV is equal to constant. So if area is increasing, velocity will decrease, and vice versa. If velocity area is decreasing, velocity will increase. And then we derived and also understood Bernoulli's equation, which is like the main important equation in fluid flow operations. So what is Bernoulli's equation? Basically conservation of energy, right? So pressure plus half rho v square, that is kinetic energy, plus potential energy will be constant. So you can also rewrite this as P by rho g, that is pressure head, plus v square by 2g, plus h is equal to constant. Okay. So you can use this Bernoulli's equation to calculate the pressure difference in a pipeline. You can also We also studied different equipments which works on this Bernoulli's equation to which will be helpful in calculating the velocity of the fluid, right? Like venturimeter or fish meter. So we'll come to that part as well. Okay, so basically this Bernoulli's equation will be applicable in many situations in fluid flow operations. Okay, and then we also understood about fluid dynamics as well. Okay, so basically we discussed about boundary layer, viscous flow, and boundary layer. And coming to some of the highlights that we discussed in this topic, we also discussed about Heisenberg-Poiseuille equation, which is again important equation which helps in calculating pressure drop in a pipeline. So, when do we use this Heisenberg-Poiseuille equation? Heisenberg-Poiseuille equation. When do we use this particular equation, or under what conditions? Will it be used in laminar flow, turbulent flow, transient flow, or will it be used in open channel flows or closed channel flows? When do we use this equation? Okay, so this is basically used in laminar flow in pipes. Okay, and then we also understood about turbulent flow, its velocity profiles, and all different energy losses that will be there. Energy losses. And then we discussed about boundary layer theory, how it is developed and how the separation happens in boundary layer, how the boundary layer is separated. Development and separation. Okay. So, do you have any doubts until this part? I think I forgot to cover few important topics. Again, going back to week one, we also discussed about Newtonian and non-Newtonian fluids as well, right? Newtonian versus non-Newtonian fluids. Okay. So, what is the difference between Newtonian and non-Newtonian fluids? So, to understand this, we need to have an understanding of something called Newton's law of viscosity. Newton's law of viscosity. That is, tau is equal to minus mu into du by dy. Okay. So, if a particular liquid, if a liquid follows this Newtonian law, then it is considered as a Newtonian fluid, and if it doesn't follow this particular law, it is called a non-Newtonian fluids. Okay, so we have different type of Newtonian and non-Newtonian fluids. So can someone give me examples of Newtonian fluids and non-Newtonian fluids, or classification of Newtonian and non-Newtonian fluids? Newtonian and non-Newtonian fluids. This is shear stress versus rate of angle deformation or rate of deformation. Okay. So if you observe this equation, this is something like y is equal to mx, right, which passes through origin. So all the Newtonian fluids will pass through the origin. Okay, for this particular graph. This is Newtonian fluid. Okay, but there will be other fluids which doesn't do follow exact behavior, right? So we have many such liquids. So one is called dilatant, and then we have pseudoplastic. Dilatants and pseudoplastics. Okay, so for all these liquids at zero angle deformation, shear stress will be zero. But there are other liquids or other class of fluids which has a certain shear stress at zero rate of deformation. Okay, so they start from a certain y intercept. Sorry, let me just read for this again. Okay, pseudoplastic, and then we have dilatant, and we also have Bingham plastics, which replicate behavior of Newton fluids, but they have a certain offset. Like at even at zero angle deformation, they have certain shear stress, which is equal to tau naught. But once you exceed this threshold of T naught, they behave similar to Newtonian fluids. Okay, and then you have thixotropic and rheopeptic. Okay, so did I miss any other classification? Okay. So do you have any doubts until now? And then we also discussed about manometers and inclined manometers, right? Inclined manometers. So what is a manometer? What is a manometer? What is a manometer? Or what is the purpose of manometer? So manometer is a device which is used to measure the pressure in a pipeline, right? So let's say we have a flow, and let's say this is flowing at v velocity, and this is having density rho and viscosity mu, and the area of this pipeline is A, cross-section area, and you want to measure a pressure, let's say at this particular location, at location 1. So how do you measure pressure at this location? You need some kind of a device, right, to measure the pressure. How do you do that? So here comes the role of manometer or YouTube manometer or inclined manometer. So whenever there is a flow, if you connect this manometer, so manometer is basically instrument which is filled with any liquid like mercury. Okay, so this is already filled with, let's say, mercury. You can also use alcohol depending upon your application. Okay, and the water flowing, it will exert a certain pressure here. Okay, so the difference between, so let's say this is height h1 and this is at the same location. Okay, so let's say this is h2. So if you want to calculate the pressure exerted or the pressure inside this pipeline, you just have to measure the height of this limb, okay, height of the liquid in this limb, and multiply it with density and gravity. You will get the pressure exerted on the other limb, which is basically the pressure of flow. Okay, and you have different variations of these YouTube manometers. You have inclined manometers, and you can also calculate. You also have differential manometers, which basically helps in calculating pressure drop across 2 points. So can someone explain me how this works? So we have the almost same arrangement, but the only change is that it will be connected across two different points. So let's say this is a pipeline and water is flowing, water or some liquid is flowing in these pipelines, and you want to measure pressure across two different points. So let's say this is one and this is two, because only when there is pressure drop across the pipe, fluid will be flowing, right. So you want to measure the this particular pressure drop in the pipeline. So you want to measure across 1 and 2 points. So what do you do? So you will be connecting manometer at one end, and you will connect the second end of the manometer to the second point. Okay. And again, depending upon the pressure exerted, so obviously at point one, pressure should be high, right? Because flow is from point flow is in direction of 1 to 2, right? So it is flowing in this direction. So this has to be at higher pressure, and this has to be at lower pressure. Okay. So this pressure exerted on this limb will be more than pressure exerted on the second limb, right? So obviously the mercury or whatever liquid that you're using inside this will be at a lower height in this limb one, and it will be at slightly higher height in the second limb. Okay, so this will be filled with water or some fluid which is in the pipeline. So if you just take the difference of height, okay, this is the effective height, right? Effective height of, or let's say the difference between the height levels of limb 1 and limb 2. So if you just multiply with density and gravity, this will give us the pressure drop. Okay, so a similar application. So in YouTube manometers, one end of the tube will be closed, whereas in differential manometers, the second end will be connected to the second point to calculate the pressure difference across two ends or 2 points. Okay. And then we also have inclined manometers, which are modified form of YouTube manometers. So inclined manometers are used for measuring very slight changes in pressure. Okay, so it looks something like a YouTube manometer. So YouTube manometer will be like this, right? So whereas inclined manometer, it will be of this orientation. Okay, liquid will be filled in this column. Okay, so the advantage of inclined manometer is that inclined manometer will be very sensitive when compared to normal YouTube manometer, and it will also be helping in calculating very slight changes in pressure. Okay, because of the inclination, even a slight change in pressure will cause the liquid to change its length or height in the manometer limb. Okay, so this helps in measuring this even the smallest changes which are occurring in the pipelines. Okay, so this is the difference between manometer and inclined manometer, and we also have different type of manometers which we have discussed in the class itself. Okay, so if you have any doubts until now, you can unmute yourself and ask me, or post them in the chat box as well. And coming to the next topic, we discussed about steady state, unsteady state, and we also discussed about uniform and non-uniform flows, and then compressible and incompressible flows. So first, let's see steady versus unsteady state. Okay, so what is steady state and unsteady state? What is the difference between steady state and unsteady state? Difference between steady state and unsteady state. So let's take an example. Let's say we have a pipeline and U is the velocity of the fluid in the pipeline. Okay. So let's say, for example, if this velocity U you are measuring across this particular point. Okay. So let's say at t is equal to 0, velocity is unchanged, that is U, and at let's say t is equal to after t seconds, velocity is again U. Then you can consider this to be a steady state, okay, because there is no change in the property of the fluid. Okay, velocity is not changing and it is kept constant for the fluid. But let's say if you're measuring the velocity and after let's say t seconds or t minutes, the velocity of the fluid changes from u to let's say u dash or u2. So that cannot be considered steady state because of property, not property, or the flow of fluid is changing, right? So you cannot consider that to be a steady state flow. So if the properties or the characteristics of a particular substance or a fluid, if it is constant over a period of time, okay, so you can consider that to be a steady state. But let's say if it is varying, then it is going to be unsteady state. Okay, and what is the difference between uniform and non-uniform flow? Uniform versus non-uniform. If I'll take the same example, let's say if u is the velocity at t is equal to 0 and the velocity remains unchanged after t seconds. Can you consider that to be an uniform flow? Can you consider that to be a non-uniform flow or uniform flow? So coming to uniform and non-uniform, so let's say if I'll take another parameter, let's say density. You can even consider velocity itself. Okay, so let's say U is the velocity and velocity of the fluid is changing. Let's say velocity of the fluid is not constant, it is changing with time. Let's say at t is equal to 0, it's u1, and it is equal to, let's say, 5 seconds, it is u2, and at t is equal to 10 seconds, it is u3. Okay, but if this t is equal to 0, this u1, if this is maintained across all the sections, or if throughout the entire fluid, then you can consider it to be a uniform flow. Okay, the property or the characteristics of the fluid should be same across the fluid. Okay, it should not be changing. So if the property is same across the fluid, then you can consider to be a uniform. But let's say at t is equal to 0, u is u1 at this location, that is at point A. Let's say this is point A, B, and C. Okay, this is the case at point A, but at point B at t is equal to 0, let's say u is some, this is UA, UB, and at point C, let's say u t is equal to 0, u is UC. Okay, so this cannot be called a uniform flow because the property of the fluid is changing across the fluid, right? So then this becomes a non-uniform state or non-uniform flow. Okay, so that is the basic difference between steady state and uniform state or uniform flow, and difference between steady state versus non unsteady state, and uniform versus non-uniform flow or state. Okay, and we also discussed about path lines, streamlines, and streak lines as well. And after this, we discussed about the continuity equation as I've told you, which is nothing but rho 1 V1 A1 is equal to rho 2 V2 A2. Okay, this is the actual equation. But if the density is constant for the fluid, then we can consider it to be V1 A1 is equal to V2 A2. This is valid if rho is constant. Okay, and then energy conservation, which is basically Bernoulli's equation. So we also Bernoulli's equation. Okay, so we also understood where this Bernoulli's equation can be applied. So flow through nozzles, orifice, or venturimeter, we can use this Bernoulli's equation and calculate the pressure drop. Okay, so that we'll discuss in a moment. And then we also derived a momentum equation using control wall analysis. Okay, and then comes Hagen-Poiseuille's equation, which is basically for flow, laminar flow in a pipe, and formula is Q is equal to pi into del P R power 4 by 8 mu L, right? And then we discussed about Reynolds number, which is rho VD by mu. So we also discussed all these parameters, and then flow through pipes. Okay. So whenever a liquid or a fluid is flowing through a pipe, there will always be losses, right? So energy cannot be conserved 100%, right? So like energy cannot be retained, right? So there might be some losses in the form of heat energy, or whenever the fluid has to overcome the frictional forces, or whenever it is passing through bends and joints, there will always be losses which are occurring in the pipeline, right? So how do you account for these pipelines? If there are these losses in the pipelines, then Bernoulli's principle will not be applicable, right? Because we are considering that energy at one location is equal to energy at second location. But let's say if in between this point 1 and 2, if there are any joints or any bends and there are also some kind of friction losses, then how can you equate energy at one location is equal to energy at the second location? So that cannot be done, right? You have to account for some kind of a correction, which is basically which basically accounts for head losses and also some kind of minor losses, which is because of bends, walls, and expansions. Okay, so let's see how do you calculate these losses. So first comes head losses. This is basically this results. This is as a result of all the frictions that comes in the pipeline. So how do you calculate? HF is equal to F into LYD into V square by 2. This is the direct formula. I'm not going into the derivation part. Okay, so this is how you'll be able to calculate the head losses. So you just have to directly add this and you'll be able to equate the energies. And then along with this, we also have some minor losses, which is because of bends, walls, and expansions. This is because of bends, walls, and expansions. And how do you calculate these minor losses? So HM, this minor loss head is equal to K into V square by 2G. Okay. So again, you'll add this to the Bernoulli's equation and you will be able to equate the energies. Okay. So any doubts until now? So next we'll be discussing about flow measuring devices. Flow measuring devices. Okay. Give me some examples of flow measuring devices. Examples of flow measuring devices. What are the examples of flow measuring devices? We've already discussed different types of flow measuring devices. Give me examples. Give me at least one example. Different type of flow measuring devices. What are the different type of flow measuring devices? What are the different types of flow measuring devices? Or give me one example of a flow measuring device. Example of a flow measuring device. Any one example. So venturi meter is a flow measuring device, right? And then we have orifice meter, rotameter, and pitot tube. Okay. There are many other pressure measuring devices. Okay. Can you give me another examples? What principle does venturimeter use or orifice meter use? On what principle does it operate? It basically works on the principle of Bernoulli's equation, right? Law of conservation of energy, and then it will be able to give you a flow rate or pressure drop across the pipelines, right? Yes or no? We also discussed advantages and limitations of each type of measuring device, flow measuring devices. There are also many other flow measuring devices. We also discussed those. So I'll just cover venturimeter now, just for a quick revision kind of thing. So we will be having a converging section and a diverging section. So there is going to be a smooth converging and diverging section. It doesn't look so. Okay, so let's say this equation. This is play location one. This is location two. So we'll measure the pressure at this location. We'll be knowing the area of this location. Okay, and this same thing we'll be doing it here. We'll be measuring the pressure here, and from there we'll be able to calculate the necessary parameter. Okay, this basically works on the principle of Bernoulli's equation. Okay, and same thing with orifice meter as well. It works on the Bernoulli's equation, and we also have other measuring devices which works on different principles. Apart from Bernoulli's equation, there are also other principles, and they'll be operating on those principles. Okay, and then we have after discussing this flow measuring device, we discussed about dimensional analysis and simulate. Okay. So why do we need dimensional analysis? Reason for studying dimensional analysis. Why do we need to understand dimensional analysis? Any one reason. It could be right or wrong. Just give me your perspective. Like, why do you need to understand dimensional analysis? Sorry. Why do you have to understand dimensional analysis? Okay, I'll leave that to you. So, so what are the methods that can be used to carry out the dimensional analysis? You can use Buckingham pi theorem. Okay, Buckingham's pi theorem. First thing, you have to identify variables. Then you have to do the fundamental, identify the fundamental dimensions. And then you have to identify the repeating variables. Okay. So on like the steps continues. So finally, you'll be able to identify. You can group them together, and then you can develop your own dimensionless numbers as well. Okay, using this Buckingham pi theorem. So there are few important dimensionless numbers. The first one is Reynolds number. So how do you represent Reynolds number? With RE, right? RE stands for Reynolds number. So Reynolds number is nothing but inertial force upon viscous forces. And then we have fluid number, which is represented by Fe. So this is inertial force by gravity force. Sorry. Then we have Mach number. Mach number. What is the formula for Mach number? Initial forces by compressibility. And finally, we have Weber number. This is inertia upon surface tension. Okay. So then we discussed about boundary layer theory. So we understood how the boundary layer theory, or let's say boundary layer, forms in laminar and turbulent flows. Laminar versus turbulent boundary layer, and how this boundary layer grows in a along a flat plate, growth along flat plate, and then how the boundary layer gets separated. And we also discussed about drag as well. Boundary layer separation, and then drag, concept of drag. Okay. So do you have any doubts until now? I'll just wait for a few minutes. If you have any doubts, you can unmute yourself and ask me, or post them in the chat box as well. I'll just wait for 2 minutes. If not, we will move on to the next topics. So this is going to be the last session for this course. Okay. So we have been through 12 weeks of course. The entire syllabus was divided in across 12 weeks where we discuss different concepts. And today it's going to be the final session. You can also consider this to be an extra session actually. After this extra session, you'll also be having NPTEL exam, right? So those who have signed up for the exam, you can prepare for that, and you'll also be getting certificates once you're done with the course as well. After exam, okay, after if you are registered for the exam, once you qualify for it, you'll be receiving the certificates as well. Okay, so I'm assuming that you're not having doubts until now. So moving on to the next topic, this compressible flow. So we just discussed about Mach number, right? What is Mach number? Inertial forces by compressibility. If you check the units, this is going to be a unit dimensionless number. Okay. So based on the Mach number, we can classify flow into three types. This subsonic, sonic, and supersonic. So if a particular fluid is traveling with a speed less than speed of sound in air, it is considered as subsonic. If it is traveling with speed of sound, it is called sonic, and if it is greater than speed of sound, it is supersonic. Okay. And then we also have area velocity relationship in nozzles. This dA by A is equal to m square minus 1 into dV by V. Okay. Okay. So then we finally come to multi-phase flow. Okay. So what is a multi-phase flow? We just discussed this yesterday. What is a multi-phase flow? It is simultaneous flow of materials with different states or phases. It is a simultaneous flow of materials with different states or phases. It can also be simultaneous flow of materials with different chemical properties, but in same phase. Same state or phase. Okay. So this this is a definition of multi-phase flow. So and this multi-phase flow has two units or two parts in it. One is a discrete phase and that continuous phase. So one phase will always be a continuous phase and the other phase will be dispersed phase within the continuous phase. Okay, so we have different type of multiphases, that is two-phase multiphase and three-phase multiphase. We have two-phase and then we have three-phase. So under two-phase we have gas liquid, then we have liquid solid and gas solid. So all these variations comes under two-phase multi-phase flow. And then we have three phase, which basically covers. I'll just give one example here. There are different types. So we have gas, liquid, and solid. There could also be gas, liquid, liquid, and other combinations as well. But I'll just stick to this for now. So coming to, we can also have different other types. That is gas, gas, liquid, liquid as well. Okay. So as we have stated earlier, as per definition of multiphase flow, it can also be multiphase can also be uh, simultaneous flow of materials with different chemical properties, but they can be in same state, right? So if we follow the definition, gas-gas system can also be counted as a multi-phase flow. An example of a gas-gas system in industrial applications is mixing SF6, use of SF6. So SF6 mixed with argon can be used as a can be used in insulated windows, and SF6 mixed with air can be used as a coolant, or sorry, can be used as a fire extinguisher. And also, eye surgeons use SF6 as a cooling agent in operations. Okay, and then we have gas liquid system. So this is one important multi-phase flow that we'll be coming across in industries. So can you give me one important example for this gas liquid operations? Any example? There are multiple examples for gas liquid operations. One example of a gas liquid operation. Example for gas liquid operations. You must have studied petroleum engineering, right? Or you must be knowing outlet of a petroleum refinery, right? Like diesel of a petroleum refinery, right? So if you look at the petroleum refinery, you will come across something called distillation unit, right? Distillation unit is basically, or let's say you have catalytic cracking or any example. Distillation process is a gas liquid operation, right? Sorry. Also, apart from this, we also have something called absorption, which helps in removing pollutants or unwanted materials from gas streams. Okay, so we'll be using gas liquid operations here. So let's say there is an air stream which contains air, or let's say there's a gas stream which contains CO2 and N2. Okay, and you want to remove CO2 from this. So how do you remove it? You'll just pass this gas or bubble this gas through a amine solution. Okay, basically a liquid solution, and then when it comes with contact with this amine solution or alkaline solution, the CO2 which is having affinity towards basic solutions it will be absorbed instantly into it will be absorbed instantly into these amine solutions or basic solutions. So as a result, the gas which is coming out of the equipment, it will be having lower concentrations of CO2 or ideally 0% carbon dioxide. Okay, so this is how you'll be able to remove pollutants or unwanted materials from gas streams. So this is one best example of gas liquid operations. So there are many other examples. Can you give me any other examples? There are multiple examples for gas liquid operations. Any example? I gave you example of absorption, distillation. Any other examples? Apart from distillation, will you be coming across these gas liquid operations in petroleum refinery? Are there any other reactions which happen in petroleum refinery which uses gas liquid operations? Any other operations or any other examples? Gas liquid chromatography. This is also an example of gas liquid flow rate or gas liquid systems. And then we also have ozonation of ammonia, dyes, arsenic. Okay, and there are also many other gas liquid reactions which happen at industrial scale. Okay, so these are all examples of gas liquid systems. And then we have gas solid systems. So can you give me any examples of a gas solid system? Any example of a gas solid system? So drying of particles, okay, drying of particles, coating of surfaces, heat treatment, blending, classifications, all these examples comes under gas liquid operations, right? Gas solid operations. So all these are physical processes, right? There will be no chemical reaction happening. But apart from this, there are also chemical reactions which comes under gas liquid, gas solid systems. So can you name any gas solid operations which is basically a chemical reaction? There has to be a chemical reaction which is actively happening during the process, which also should involve gas solid reactions or should involve gas solid system. Sorry. Any example? No? Okay, so roasting of ores is also example of gas solid reaction. Combustions, they come under gas solid reactions, gasification, coking, calcinization, carbonization, fluid coking, catalytic regeneration. All these examples comes under gas solid reactions. And then we also have liquid systems. Okay, so liquid systems, there again, oil in water is a system. So this is basically used for flow of emulsion of oil and water in pipelines, and also extraction of organic contaminants from wastewater also comes under liquid operations. And then we also have different type of contactors like packed columns, pulsated columns, and steeled column reactors, which are used in various applications, which basically use liquid operations. And then finally we have liquid solid systems. So hydraulic conveying of solid waste, solid materials comes into liquid solid operations. Then we also have crystallization of solids, which basically involves liquid solid operations. And also slurry flows, they also comes under liquid flow operations. This is about two-phase, uh, multi-phase flow. And then coming to three-phase systems. So three-phase systems can be of different modes, that is gas, liquid, solid, gas, liquid, liquid, and solid, liquid, liquid. Okay. So what is the example of a gas, liquid, and solid operation? Gas, liquid, solid reaction or system. So if you perform any reaction between liquid phase and gas phase, so let's say A plus B is giving rise to some product, let's say D plus C plus D. So if A is gas and B is liquid, it could be vice versa as well. And if this reaction is happening in presence of a solid catalyst, this comes under a gas, liquid, solid system. So examples could be any biochemical process or hydrotreating, hydroprocessing, fluid bed catalytic cracking. So all these examples comes under three-phase system, which basically involves gas, liquid, solid systems. And coming to gas, liquid, liquid operations, so we have very common flows of oil, water, and natural gas, which is found in uh, condensation or evaporation of immiscible liquid mixtures. Okay, that is the example of a gas, liquid, liquid operation. And then solid, liquid, liquid. So if you mix sand with oil and water, that will become a solid, liquid, liquid operations, which is a three-phase flow. And then finally we have a four-phase flow or four-phase system. So one example could be liquid, liquid, gas, solid operation. The best example would be freeze desalination process where butane liquid is added to saline water, which results in the formation of ice cells. So here butane liquid is a liquid, and then we have water as liquid, gas is butane vapor, and solid is ice. So thereby forming a four-phase system which involves liquid, liquid, gas, solid operation. Okay. But what is the necessity of learning all these things? Like, why do we have to learn about different phases, like multi-phase flow? What is the reason behind learning these multi-phase flows? Sorry. And where exactly do you apply this knowledge of multi-phase flow? Where exactly do you use the knowledge of multi-phase flows? So if you look at different industries, okay, in most of the industries, you will come across at least a two-phase flow, okay, which is basically again multi-phase flow. So if you have good understanding of a multi-phase flow, you will be able to better understand or you'll be able to design efficient multi-phase unit based on knowledge, okay, based on knowledge of hydrodynamic parameters, heat transfer characteristics, mass transfer characteristics, and modeling of multi-phase flows. So, mo you need to have idea of how the flow regime works. You need to have idea of phase fractions. You need to have an idea of particle bubble, and particle droplet interactions. You need to have idea of turbulence and flow structures, mixing, distribution, okay, and how L by D ratio affects the flow. Okay, so you need to have all these ideas in order to Design an efficient equipment or efficient unit for a multi-phase flow. Okay. And then I think most of the concepts we have already discussed, I guess. So if you have any doubts, let me know. I'll try to answer them. If not, we'll end this here. Okay, I'll stay here for some time. So if you have any doubts, you can post them in the chat box or unmute yourself and ask me. So if you don't have any doubts, we'll end the session. So I'll be there online for a few minutes. So if you have any doubts in the theory part or in the problem session, you can unmute yourself and ask me or post them in the chat box as well. Regarding hall tickets, I have no idea. I'm not sure how you'll be getting those hall tickets. I think you have to contact the NPTEL team or someone from the forum. I think they might be helpful in this regard. Please contact someone from the forum. Like you'll be having a forum for this course, right? Please contact them. I think they'll be better in helping you with it. So in multi-phase flow, we also discussed about different flow patterns, right? How the flow patterns are formed and how does the velocity of liquid and gas affect these flow patterns, right? Like if you increase liquid flow rate, how does the flow pattern change? And how if you change the gas velocity, how does the flow pattern change? We also discussed this, right? We discussed this in both horizontal pipe and also in the vertical pipe. Okay, like there will be slight difference in vertical pipe. You can also see the effect of gravitational force. Okay, and we also discussed about different patterns, different factors which will affect the flow patterns, like dynamic variables. There are geometric variables which affect the flow patterns. There are thermodynamic variables which affect the flow pattern. There are physical properties which affect the flow pattern. So coming to thermodynamic variables, we have flow rate, phase fractions. All this comes from dynamic variables. And geometric variables, they are like diameter, length, shape of shape of the pipe, particle size, the hole size of the phase distributor. All these things comes under geometric variables which affect the flow pattern. And we have dynamic variables like pressure and temperature and physical properties like density, surface tension, and viscosity, which affect the flow pattern. Okay, and then we also discussed about flow pattern map, which is basically a graphical representation of boundaries or transition between different flow patterns. Okay, so we know that like when you change the flow rates, the flow pattern also change, right? So we'll just put that into graphical representation. Like we'll take superficial velocity of liquid on one axis and superficial velocity of gas on the other axis, and then we'll try to plot a graph on like at what range of velocities which type of flow will be existing. So we'll try to have an idea of that. So that is called flow pattern map. So we understood flow pattern map and we also drew it for horizontal pipe and also vertical pipe as well. And then we also discussed about the volume fraction or hold up of a phase. So which is nothing but volume of that particular phase divided by total volume. So if you want to calculate volume fraction of dispersed phase, we just have to take ratio of volume of dispersed phase to that of total volume. So that will give us volume fraction of dispersed phase. And if you want to calculate volume fraction of a continuous phase, we just have to take ratio of volume of continuous phase to that of volume of total volume. So that will give us fractional volume fraction of continuous phase. And similarly, using that, we also calculate gas holdup and liquid holdup as well using the same formulas. And then we also discussed about bulk density, viscosity of a mixture of multi-phase flow. And then we understood about superficial and interstitial velocities and how to calculate other quantities using one quantity. We also understood about slip or relative velocity, frictional pressure drop, and its analysis. Then we also understood phase interactions, and then we also derived how to calculate bubble or droplet rise velocity. Then we understood about bubble-bubble coalescence, which is basically bubble-bubble interactions, and then its breakup as well. And then we understood the maximum stable size of a bubble or drop in a fluid, in a multiphase flow, and how to calculate different formulas for calculating maximum size of a bubble. And then we also studied about interfacial area, which we also again went through the four different formulas for calculating it. And then we also studied about mixing of phases. And then lastly, we also saw applications of multiple phases, so multi-phases. Like we deep dived into different applications like absorption. As I've told you, we will be using amine solutions for removing carbon dioxide from a stream or some kind of effluent, right? So we the deep dive into these examples, like how a process operates, like how does a absorption of carbon dioxide operate, like which type of flow we'll be using. So in this case, we'll be using a bubbly flow. Okay, so how does it affect absorption? All these things we have covered in applications part. So we went through different applications like absorption of carbon dioxide is one example, and then we also went through sterilization process, which is basically done by a bubbling two-phase flow. And then we also studied about desalination of seawater. Like we deep dived into the process and like which phase, what are the different type of phases that will be there. Like how does multi-phase flow help in desalination of seawater? And then we also studied about ammonia removal by from wastewater by ozonization. Then we also we studied decolorization of dye in textile wastewater, how it is done, which type of flow is used, and what is the role of multi-phase flow in that particular operations. And then we also saw de-inking process by a two-phase mixing. And we also studied about treatment of oily wastewater, which again involves multi-phase flow. Okay. And then we also saw different gas solid flow applications like coal combustion for power generation, vinyl chloride production, polymerization of olefins, and then we also saw solid gas operations. How does it actually operate? And then we also saw urea granulation, which is again a solid gas operation. And then we also studied about other gas solid operations, which is basically silicon production, nanoparticle coating, and then hydrocracking, cracking of hydrocarbons, gas phase polymeric reactions, coating of metals and glass objects, drying of solids, roasting of foods, coating of pills, granulation. All these examples comes under gas solid operations. Then combustion, gasification, pyrolysis of waste wood, chemical loop combustion, all these operations comes under gas solid applications. We also saw how these operations work. And then we also studied about liquid operations, gas liquid operations. Okay. So that's how our 12-week course went. So we went through each and every application as well. Okay. So yeah, that's it from my side. If you have any doubts, please don't hesitate. This is going to be the last session. So if you have any doubts, try to unmute yourself and ask me, or if not, you can also post them in the chat box as well. I'll try to answer them. Any doubts, be it related to theory part, or maybe it could be related to the problems which you're trying to solve, or which were already discussed in the class. If you find any difficulties even in the problems, you can ask me. I'll try to answer them. If you don't have any doubts, then we can end this session here. Okay. Thank you, everyone. Thank you for attending the session.